The first thing that we're going to look at is the difference between a continuous function and a discontinuous function. So the function on the left-hand side is a continuous function. And if you look at the graph, it's one graph. There's no holes, there's no jumps, there's no breaks. If you were to draw this graph with your pen, you wouldn't pick your pen off the paper at all. It would just be a continuous motion. For the discontinuous function, as the name says, it's discontinuous. So it doesn't continue. It has jumps, it has breaks. You can't draw the entire graph with your pen on the paper. You have to draw the left side, pick your pen off the paper. Draw the middle parabola, pick your pen off the paper, draw the right-hand side. If we look at the denominators of each, the denominator of the continuous function, if we try to set this to 0 and we want to find the restrictions, when I subtract 9 on each side, I get x squared equals negative 9. And I know that that's going to give me an imaginary number. So when I take the square root, I get plus or minus 3i. So that has no restrictions. There's nothing that's going to make that denominator 0. Since there are no restrictions, it's a continuous function. For the discontinuous function, if we set that denominator to 0, we're going to get two restrictions. So 2x plus 3 equals 0. We'll get negative 3 halves for x. So x can't be negative 3 halves, or x can't be 1. So since there are restrictions here, it's a discontinuous function. So a discontinuous function can have vertical asymptotes. So if we look at this graph, this function, so what are the vertical asymptotes of the following function? So we know from the lesson from the previous class with the iPads that the vertical asymptotes are what makes the denominator 0. So if we look at the denominator and we set it to 0, we have x minus 2 equals 0, which would give us x equals 2. And then we have x plus 3 equals 0, which would give us negative 3. Now, if we graph this function, it's going to look like this. So we said that x basically can't equal 2, that's a restriction, and x can't equal negative 3. So if we look at this graph, when x is negative 3, right, there's nothing here. So I'm going to draw a dotted line here. When I go to x equals 2, if I draw a line, well, the graph's going right through that. So there's no asymptote here. So why is there not a vertical asymptote? So I know for a fact that I have a vertical asymptote at x equals negative 3. But I don't have one at x equals 2. If we look at the function again, can we simplify it? Well, we know we can cancel out things that are exactly the same. So the x minus 2's are going to cancel out. So what this leaves us with is a 1 in the top and an x plus 3 in the denominator. So what we've had here is points of discontinuity. So this little box is going to explain the differences between the two types of discontinuity. So basically, there's two types of discontinuity. So you can have removable or non-removable. And the names mean exactly what they sound like. So if you remove something, it's removable discontinuity. If you do not remove it, it's non-removable discontinuity. So if we look at the function that we just simplified, we got rid of the x minus 2's. We canceled them out. So we removed them. So we have removable discontinuity at x equals 2. So whatever we remove, if we set that to 0, x equals 2 is a removable discontinuity. And when you graph removable discontinuity, we know that a non-removable looks like an asymptote. That's a vertical asymptote. If you have a removable, it's represented by a hole in the graph. So it's going to look like there's nothing affecting the graph at all. So if we go back to this one, it doesn't look like anything's happening at 2. So when x is 2 or here, it looks like nothing's happening. But really, there's a little hole there. So at 2, it's undefined. So this is going to represent a hole. And the hole is actually a point. So the point is not actually on the graph. That's where we're going to have our hole. So we're literally going to draw an open circle at a certain point. And to find the value of that point, we're going to take the x value that was removable, which was 2, and we're going to plug that value into the simplified function. So the simplified function is this 1 over x plus 3. If I plug 2 into that, 1 over 2 plus 3, that gives me 1 over 5. So I have a whole at 2 1/5. So what I basically did was I took what the removable discontinuity was, and I plugged it into the simplified function, and at that point, I'm redefining that point. So it's not actually going to be part of my graph, but at 2 1/5, I have a hole in my graph. I have a little open circle. So I have non-removable, where I didn't remove it. So it's non-removable at x equals -3. And that's represented on the graph as a vertical asymptote at x equals -3. Okay, so two types of discontinuity, removable and non-removable. Okay, removable is a hole, non-removable is a vertical asymptote. So what are the domain and points of discontinuity of the rational functions? And are the points of discontinuity removable or non-removable? So first thing that we want to do is we want to factor. So we're going to look at A. So on A, we want to factor anything that we can first. So I'm going to factor the denominator to be x plus 4, x minus 4. So we're just using difference of squares. So I can't cancel anything out here. To find the domain are all the values that x can be. So when we're doing our domain, we're going to say it's all real numbers except for the restriction, so whatever x cannot be. So the restrictions on this one would be -4 and +4. So the domain is going to be all real numbers except x cannot equal -4 or +4. Okay, there is another way that you can write the domain. As long as you know how to write it this way with the all real numbers and the restrictions, that is completely fine. I'm just going to show you the other way, just so if you see it, don't freak out. It means the exact same thing. The other way that you can write the domain is, we would say it's from -infinity to -4. Okay, so everything between -infinity and -4 with a round bracket, meaning it doesn't include the -4. This U, it means in union with, so it means additionally, from -4 to 4. Okay, so again, they're both in the round brackets. It's not including -4, it's not including +4, but it's everything in between. And then in union with, 4 to infinity. So again, not including 4, but everything from 4 and up. Okay, so you don't have to memorize this way of writing it. You may see it in the future. You may see it this year, like in the book or something. So just be familiar that it's the same exact thing. So I didn't cancel anything out. There was nothing to cancel out. So I have non-removable discontinuity. So I have non-removable, and it's at x equals -4 and x equals 4. All right, so if we look at the next one, again, we want to factor anything that we can. So if we look at B, y equals, I can factor the top, x plus 1, x minus 1. The bottom, I can't factor, so I'm going to leave it x squared plus 3. So if I try to set the denominator equal to 0, I'm going to get an imaginary number. So this is a continuous function. So my domain is going to be all real numbers, since there is no restriction. So domain would just be all real numbers. And this function doesn't have any points of discontinuity, so it's just a continuous function. Okay, and then for C, again, we want to factor anything that we can. So x plus 1 is on top. On the bottom, multiplies to 2 and adds to 3. We can use 2 and 1. So from here, we can cancel out the x plus 1s, and we have 1 over x plus 2. So to find our domain, again, we're going to say it's all real numbers except for the restrictions. And just like before, when we were just simplifying and multiplying and dividing and adding and subtracting, Even if you cancel something out, it's still a restriction. So the domain is all real numbers, except x cannot equal -2 or -1. Now, since I removed the x plus 1, I have removable, removable discontinuity, removable at x equals -1, and I have non-removable at x equals -2, since I did not remove that. Okay, so we're just going to look at a couple of other examples. If you're good with it, you don't have to watch these. If you just want to see a couple of extra ones, they're here. I'm going to go through these rather quickly. Okay, so we just want to find the points of discontinuity. So again, I'm going to factor. So for the first one, I'm going to factor my denominator to be x plus 5 and x plus 4. I can cancel out my x plus 5s. So I have 1 over x plus 4. So this has removable. And it's removable at x equals -5 because I took it out. And I have non-removable at x equals -4. For number 2, again, I'm going to factor everything that I can. So x plus 2 on the top. On the bottom, I have x minus 9, x plus 2. I can cancel out my x plus 2's, so I have x over x minus 9. And I have removable at x equals -2, since I took out the x plus 2's. And I have non-removable at x equals 9, since I did not remove that. Okay, so for 3, I'm going to see if I can factor, which I can't. Okay, it's already factored for me at the bottom, so x plus 1 squared. Nothing's going to cancel out, so I just have, non-removable at x equals -1. And there's no removable since nothing was canceled out. And then with the last one, again, I'm going to factor. So I'm going to use -2 and +1. And then the bottom of this one, I have to do the long way because a is not equal to 1. So if you do it the long way, you'll end up with 3x minus 1 and x minus 2. So I can cancel out the x minus 2's, and I have x plus 1 over 3x minus 1. So I have removable at x equals 2, since I canceled out the x minus 2's. And I have non-removable at x equals 1/3. Because 3x minus 1, if I set it to 0, I get 1/3.